So good afternoon to everyone. Good morning, Professor Randy in Hawaii and Larissa. Everyone welcome to the Astronomy Department of the Institute of Astronomy of University of São Paulo. Thank you all for your participation in this seminar of your astronomy department. And today we have the pleasure of having the presence of Professor Randy Campbell. He's Science Operation Lead Astronomer at the Keck Observatory in Hawaii, in US. Professor Randy, thank you very much for accepting this invitation, for being here today with us. And I would like to share with you some information about Randy. He's part of the Keck Observatory staff for over 28 years. And he leads a team of scientists and operators that provide visiting astronomers with observing support for using the Keck telescopes. He has technical expertise in developing and maintaining instrumentation of the observatory, in particular the laser-guided star adaptive optics. Professor Randy's research includes the study of classical nova, and he's also a member of the UCLA, the California University in Los Angeles, Galactic Center group, where he contributes to studies of the gas and dust near the galactic black hole. And he also develops tools for three-dimensional visualization of data. And today, Professor Randy is going to present the talk, the Swansong of the Galactic Center source X7. And questions can be addressed to Randy after his presentation, unless he says he asks us to make questions during the presentation. And if you are following the seminar via YouTube, you can also chat your questions. We'll pass to Professor Randy. And I would like to ask all the colleagues connected to Google Meet to please turn off your cameras and microphones before the seminar starts. And Professor Randy, feel free to start, and whenever you're ready.
Okay, well, thank you very much for that introduction, Rinaldo, and thank you to the organizers for creating this opportunity to present today. It's really an honor and a pleasure to be able to do this. And today, I'm going to be presenting some work I've been doing over the past few years with a group at the University of California, Los Angeles, as Rinaldo mentioned, the so-called Galactic Center Orbits Initiative Group, GCOI. And in particular, an early career scientist, Anna Churlo, who is the first author on the paper that we wrote together on these results. And you can see the reference there. It's AppJ that we just published this year. And Anna was a visiting postdoc a few years ago as part of our visiting scholar program. And it was a real excellent project that we were able to collaborate on this work and some other work. And currently I'm working with another visiting scholar, Dr. Larissa Takeda from São Paulo. And so it's through my association with Larissa that I'm able to give this presentation to the Institute today. And again, I thank Dr. Takeda and the organizers for this opportunity to present. Okay, so before I get into the science, maybe just a little bit more about Keck and what we do. And so Keck, of course, is two 10-meter telescopes on the mountain known as Mauna Kea in the big island of Hawaii, or the island of Hawaii. Mauna Kea is a almost 14,000 foot or nearly 4,000 meter mountain. So it's above much of the clouds and lower atmosphere, and it's an ideal site to have a telescope, especially in the northern hemisphere. And so the Keck telescopes have been in operation now about 30 years, and I've been a part of the observatory 28 years. And I joined as a technical expert, mostly to work on instrumentation and adaptive optics. But I also am able to do a little bit of research, what I'm going to talk about today. So the novel thing about Keck is that it's made out of a segmented mirror. The primary mirror is 36 hexagons, and they're each about 1.5 meters in size. And by dividing the primary mirror into segments, you're able to scale it up into larger sizes. And of course, the future extremely large telescopes are all using this approach. And so this innovation is largely credited to a person named Jerry Nelson. And in the late 70s and early 80s, he solved a lot of the technical problems that have to do with keeping the segments to act as a single primary mirror. And of course, it was a huge risk, but it works and works extremely well. And so Keck has been one of the most scientifically productive telescopes on the ground-based observatories since then. I also work on instrumentation. Two of the instruments that I'm associated with and are acquired the data that I'm going to be presenting today. One of them is known as NERC2. It's an imager that uses adaptive optics and is an infrared camera that is sensitive from 1 out to about 5 microns into the mid-infrared. And the other infrared instrument is an integral field spectrometer known as Osiris, and it's limited in bandwidth to the near infrared, but it's a very powerful instrument, and I'll show you some interesting data from that instrument here in a little bit. And of course, we use adaptive optics to get the highest spatial resolution that we can out of our 10-meter telescope. And this is just a little cartoon that shows how the adaptive optics works. You have a star that you use some of the light that's split off to a wavefront sensor, and then that controls a deformable mirror that cancels out the distorted wavefront and the distortion caused by the turbulence in the atmosphere. If you have a bright natural guide star, it works great. It's near your field, but if you don't, you have to use a laser instead of a bright natural guide star. And so we have a couple of sodium lasers that laze at 589 nanometers, and they fluoresce sodium atoms in the upper mesosphere, and that creates enough of a bright point source that we can use for adaptive optics, an artificial star, if you will. So this is a nice picture of those lasers pointed up. Both of them are trained on the center of the Milky Way galaxy and the center of the galaxy. So they were both studying that on this particular night. And you can see the dark bands of the Milky Way there, and pointed right at the center. And that's what I'm going to be talking about today is some gas and dust near the center of the Milky Way, the dynamical center. And so in the immediate dynamical center of the Milky Way, of course, there's a supermassive black hole, which was established, due to the study of the orbits of the stars around that star, around the black hole. I'll talk about that a little bit more. But there's a bunch of clusters of stars, young and old. There's streams of gas, and the center of the Milky Way is a relatively quiet nucleus compared to other galaxies, and one of the things we're trying to understand is why it's so quiet. And one of the ways we do that is by studying the gas and the dust in the immediate vicinity of this black hole. And as I pointed out earlier, the center of the Milky Way is behind a thick layer of dust that attenuates the visible light by around 30 magnitudes. But luckily, the infrared light is able to transmit through the gas and dust, and that gives us an ability to study that. Because the region is so dense with very dense clusters of stars and other material, without the high spatial resolution, everything is confused into a blurry mess. And so without the adaptive optics and without the high spatial resolution of a 10-meter telescope, some of this work can't be done. So all these things have to come together. The large 10-meter telescope on a great site like Mauna Kea, being able to do the work in the infrared to get through the gas and dust, and to have the high spatial resolution afforded by the laser guide star adaptive optics. All those are necessary elements in order to conduct some of these studies. And then you need the instrumentation. We have examples of a NERC2 image in the bluish frame, and that's showing some of the thermal infrared coming through. And then Osiris is an integral field spectrometer, so you get both imaging and spectral information all in one data product or a data cube. So you get a spectrum at each pixel, and then you get an image at each wavelength that you're interested in, up to a spectral resolution of around 3500. So it's a very powerful way to study the dynamics and some of the chemical signatures, et cetera, that come through in the spectra. Okay, so of course, a lot of work has been done in this region in the Galactic Center, and many groups are studying the center of the galaxy. And after 15 years of Osiris data and even more years of imaging data at high resolution, it's been well established that there's a supermassive black hole that is the radio source Sag star that's roughly 4 million times the mass of the sun. And this earned a Nobel Prize for Andrea Ghez at UCLA, and she is the director of this Galactic Center group that I'm a member of. And so we're all very proud of this achievement. But the studies continue on beyond the establishment of the black hole. We're studying some of the stellar clusters and the young and the old, and we're trying to understand the population of these the stellar populations that's going on. And then we also have used one of the stellar orbits to do a test of general relativity with this star called SO2, which during its closest approach had a redshift, a relativity influenced redshift change, and that was published recently. And so it's a nice test of general relativity. Another interesting thing is back in 2012, a couple of interesting objects known as G1 and G2 were very excited to see go in closest approach to the black hole, and originally thought that the G2, being a little gas cloud, would be consumed by the black hole, would be accreted, and there would be some interesting effects due to that accretion event. But it turns out G2 just went whizzing right on by and is now still doing just fine. And so it must be a massive object in its core. But it's interesting, and it doesn't look like a star. It looks like a gas cloud. And we've since then found some other things that that are similar to that, and I'll get to that in a second. All right, so now on to these data that we have with NERC2 and Osiris. Osiris, again, is an integral field spectrometer, and one of the things that we can do with that integral field, since it's a three-dimensional cube, is look at it with a three-dimensional visualization tool. And this is very helpful in distinguishing different features that are have different velocities and different emission features of the gas, and we're able to separate those from the stars. And so this is a 3D tool that we developed to help analyze not only these data, but we use it on other things like the classical nova studies that Larissa and I are working on in a separate study. But it's a nice tool, and it's been useful for some of this, as I'll show you here. So this is now a data cube of the Galactic Center, and in the center part of that cube, you're seeing bracket gamma emission, and you're seeing some structure in that bracket gamma emission. This is a broader bandwidth of a filter in Osiris called KN3. It's the part of the K band spectrum, and this is a hydrogen recombination line in the center, and then there's H2 emission towards the left part of the cube that you're seeing. Now, if we didn't have the stellar continuous subtracted, it would be hard to see this bracket gamma emission. In fact, this is what it would look like as a raw data cube. But one of the things that this tool will allow us to do is subtract out the continua from the stellar sources, and then we can see the gas emission. And so it's a nice way to highlight what we're trying to study, which is the gas in this case, gas and the dust. So now if I zoom in on just the bracket gamma emission, you can see a lot more detail in the features of the bracket gamma. And so what we're seeing is, let me get this cursor going here. Okay, so if you're seeing my laser pointer, there's a lot of bracket gamma. Okay, thanks. There's a lot of bracket gamma emission at the rest velocity, or a zero velocity, and that's in the center of this frame. But you're also seeing some features that have relatively high velocity. There is some residuals from the stellar subtraction, and that's along these lines here. Some of the brighter stars, it's harder to get the continua cleanly subtracted. But what we found is there's some compact sources that are in addition to that one that I mentioned earlier, G2. So we have some other G objects that are these compact sources that look like gas blobs, but they behave more like stellar massive sources. And we published a paper on this a few years ago. Again, this was Anna Chirlo in 2020 on these additional G objects. And we think there's a whole class of these G objects. But then there's this other more extended feature that is a higher blue shifted linear extended feature called X7. And that one we didn't consider as part of the G class of objects, and now we're studying X7 as its own independent feature, and that's what I'm going to talk about today. I'm finally getting to the subject of the talk. So this is X7 that really stuck out in this three-dimensional view of the integral field spectroscopy. X7 is also a dust source. It's got some warm dust associated with it, and if you look at an image in now this image is a 3-color image from the instrument NERC2, and the 3 colors are assigned to the bandwidths of the K, L, and M band of the NERC2. These are K is 2 microns, L is 3 microns, and M is the 5 micron filter in NERC2. And so the cooler dust objects are showing up as red in this image, and X7 is this thermal dust emission, and you can see very dramatically this linear feature here. So the black hole is at Sag star. This image was taken when Sag star was relatively quiet, although it is showing some thermal emission in this image. And then you see a lot of other known features of the gas and dust. This is the so-called northern arm, which has a extended spiral feature. If you could zoom out, our NERC2 image is zoomed in very, very closely. As you can see, this is only 1 arcsecond scale shown here. There's another extended feature down here called X3 that's in this frame. Originally, these objects were named for their so-called bow-shocked appearance, and you can see as X3 looks like maybe a stellar source that's being blasted away by some wind, and you see a shocked bow shock forming around that. And X7 was also thought to be a bow shock object. We no longer think that, because in later years it's become more and more extended and has lost its bow shock appearance, and I'll show you that in a little bit. This is some other nebulous feature called epsilon. There's a big cavity of a lack of dust and gas down low, and that's known as the mini cavity. Just to kind of orient you here on what's going on. So this is a very high spatial resolution image. You're seeing a lot of individual stars, and it's these data that helped establish the orbits of these stars around the black hole and led to the confirmation of the supermassive black hole. But we're reprocessing the data over the last 20 years or so in order to study the gas and the dust. Okay, so moving on, I'm gonna need to get going here because of the time frame. And so now I'm showing NERC2 images over a course of about 20 years, and they proceed from early on in 2002 up to 2001. And this is to show that X7 has a lot of proper motion. It's near the center of the frame here. To orient the black hole is up in the upper left corner of these frames. And as you march along, the object is moving to the north, mostly. This can also be shown in an animation of these same data. As you see, the object not only has high proper motion, but it's also changing in morphology. It's being stretched out and becomes longer over this time frame. This can also be shown in the Osiris data. So Osiris gives you imaging and spectroscopy in one data cube. And so this is a bit of a busy plot here. Let me unpack it a little bit. So in the gray scale frames, you're seeing imaging data of bracket gamma emissions. So we've cut out just the part of the cube that has X7 blue shifted bracket gamma emission to show you images of X7. The color plots are radial velocity maps of X7 to show you the radial velocity structure. So the colors go from minus 750 kilometers per second down to minus 500 kilometers per second. So it's all blue shifted, but it's scaled by color according to these velocities. So the tip has a higher velocity, higher blue shifted velocity than the tail of X7 in these early years of 2006 or so. But that velocity structure changes as the object moves and stretches out and becomes longer. And by the time you get to recent years of 2019, 2020, the tip has a lower velocity than the tail. That's also shown in these velocity profile plots. So I've taken where you see the green line along X7 here, I've shown the velocity along that line, along the ridge of X7, and you see that the velocity profile inverts over this past 20 years or so. That is, that the tip was the highest velocity point in 2006, but by the time you get to 2021, the tip is the lowest velocity point, and the tail, so that the tail hasn't changed much in velocity, but the tip has changed dramatically as this object moves to the north and closer to the black hole. So we can use the proper motion and the radial velocity data to fit an orbit to the tip of X7, and we've done that. And what we can see is that the tip, anyway, behaves as though it's coming out of the page at a pretty high velocity and is moving in an orbital motion around the supermassive black hole, and is behaving pretty consistently with this orbital motion that we are able to measure. Now, one of the interesting things about the morphology and the shape of X7 is we would kind of expect, if it was a bow-shocked object, that the tail would be oriented according to a wind from Sagittarius star or from the orbital motion. But what we find is that the angle of the extent of X7 does not change appreciably over this 20 years or so, and you would expect it to change on the order of 30 degrees or so, and we're not seeing that change. If it were oriented to Sagittarius star, it would change by 30 degrees. So the orientation of the tail of X7 is not aligned either with its orbital motion or with Sagittarius star. So we don't think that the tail is caused by a wind from Sagittarius star or from its own velocity, direction of velocity. We also don't see that we checked on what we know about some of the magnetic field lines in this region, and although the resolution of the magnetic field lines is not as high enough to confirm or deny, to establish for sure that it's not aligned with magnetic field lines. We can't say that for sure, but what we know is it doesn't look like it is. In fact, it looks perpendicular to what we know about the magnetic field lines. And we've used some models of winds from the nearby massive stars to see if that might explain the orientation of X7. And again, those models do not help us understand the extended tail of X7. So we've been able to rule out a few things that explain why X7 looks the way it does. We've also compared the proper motion of X7 to some of the nearby stellar sources and also some of the nearby G objects that we've studied. And we don't see a strong association with any of the other objects that we know of. There was a publication a few years ago, Feisker et al. 2021, that claimed that SO73 was the source of X7. And although we can't completely rule that out, it doesn't look like SO73 is the source of X7. It has a very different proper motion, and its orientation is becoming less and less associated with it. So we think it's just a random alignment. X7 is a big, long, extended feature, and it's moving quite a bit on the sky. And this is a very dense region of stars, and so it's likely for X7 to pass over a few stars during this time frame. And so we don't think it's necessarily associated with this stellar source. One thing we are able to do is use a simple model of basically a string of points along the ridge of X7, and give them each an independent orbit model, and so that they have similar orbit, except just a different separation from the supermassive black hole, and then model their motion independently, and so that they're only influenced by the gravity of the black hole, and they're not influenced by the gravity of each other. And so they're independent points. And this duplicates what we see pretty nicely, even though it's a very simple model. It shows that the orientation of X7 behaves similar to what we expect. You're seeing the colored points are the model, and the gray lines extended along here are what we measure as the orientation of X7 as it moves over this time frame. And so it agrees pretty well, and it also duplicates this inverted radial velocity profile that we have observed, whereas the tip starts out at these higher velocities and then moves into. So we think this is basically a linear gas and dust feature that was created by who knows what, and was propelled on its way towards X7, or towards the supermassive black hole, and is now being tidally stretched and ripped apart by the tidal forces of the supermassive black hole. And if you model that with just a string of independent points, the projection effects and the radial velocity profile are duplicated fairly well. Now, that what is the source of X7? We don't know. We can speculate on, several different things that might have propelled this gas and dust feature hurling towards the supermassive black hole, but that would be just pure speculation. We don't have any confirmed way of telling for sure what that source is. So I'll start to then wrap up now with my conclusion slide, and this is just to go through the points real quick. We detect this thermal emission and gas emission from this interesting feature. We're able to see a lot of proper motion and changes in the radial velocity due to acceleration forces from the black hole. We think that tidal forces are acting on this thing to cause the stretching, and what we're starting to see is it breaking up a little bit. We think it'll continue to break up, which is why the title of this talk is the Swansong of X7. We think it will continue to get ripped apart into independent things. Won't necessarily be accreted onto in any time soon. We think that it doesn't have a real close approach to the black hole, and according to our orbit fit, it'll approach in about another 30 years, but not close enough to be accreted. So it'll probably just continue to get ripped apart and swirl around the black hole over the next few hundred years or so. And we're able to rule out some things that explain that were proposed to explain the shape of X7, which is that it was a bow shock due to winds or magnetic field lines, but we don't think that that's what's going on. And so our simple model agrees pretty well with the observations. And with that, I'd like to thank the organizers again for the opportunity to present this talk, and I will stop there and take some questions. Yes, that's an excellent question, and we struggled with that quite a bit. And what we decided to do was focus on just the tip. So we made a definition of the tip, which we made a measurement of the profile of the intensity at the tip, and we measured where the half power point of the leading edge of this feature was, and we define that as a point along the leading edge of the tip. And so our orbit fit is only to that tip. And but then we used some of those orbit parameters and extended those to, in our model, then we gave orbits to independent points to see if that helped explain what we were seeing on the extended features. But the fit to the orbit, the measurement of the proper motion and the measurement of the radial velocity changes is only on the tip. So it's just a point that we defined as the half power point of the leading edge of the feature. Yes, there's I think it's an open question. I think that G2 is a very interesting object in its own right. It whether it has a stellar massive source or a core or not is still being debated. We think that because it survived closest approach and is still detectable as a relatively compact object in both the thermal infrared and in the bracket gamma emission, we're still seeing it as of today. So it survived its closest approach, and the thinking is because of that, it must be gravitationally bound material to some kind of massive core. Now, I was just going to say in X7, because of its different appearance and morphology, we think is not necessarily has a massive core. Some of the other G objects, which are compact and again behave a little bit more dynamically like stars, although they don't. The one difference is they don't have a stellar continuum. All the stars, even the faintest stars that we detect, are clearly stellar sources with a stellar continuum. What distinguishes both the G objects and X7 is they do not have a detectable continuum at any wavelengths. And so only in the thermal longer wavelengths at 3 and 5 microns, but not in K or H band. And so that's what distinguishes them, is that they don't have that stellar continuum.
Exactly, much less than a star, than a solar mass.
Exactly.
Okay.
Exactly.
Thank you very much.
Thank you. Siriaco, questions? I think Elizabeth, she will make a question from Google Meet.
Hi, thanks a lot for this very interesting talk. I have a question regarding the potential nature of this object. What is the distance from the center from the center, from Sagittarius, approximately?
Let's see. I have to try and remember what that is. Yeah, I'm sorry, I don't remember the exact number. I have to look that up in the paper. But let's see. We've talked about it in different units, but I think it's on the order of a few thousand to 10,000 AU or so.
Okay. So it's quite close to Sagittarius, right? Could it be part of because there is this molecular, this dust and molecular disk around the center of the galaxy, around Sagittarius, the supermassive black hole. And this distance is suggestive that it could be part of this material. Is that possible? And the other possibility is, could it be a remnant or a slice of a spiral arm component?
Yes, that is one of the possible suggested sources of this feature. And one of the terms that we jokingly use is space junk, where it has been somehow separated off from these spiral features. There's the northern arm that I showed. Let me see if I can pull that image back up again here real quick. Yes, so there's this feature called the northern arm, which is a larger spiral feature that extends out many arcseconds or arc minutes,
right, and
is part of a larger scale structure. And it has similar observables in terms of emission lines and dust emission, thermal emission, and has similar velocity structure. It has the tip of this northern arm is also highly blue shifted. And one of the ideas is that somehow X7 has broken off from that, or maybe from epsilon or some of the other gas and dust features that you see. So here's the northern arm, and this tip here is like I say, it's has a similar velocity structure. So maybe something, accelerated X7 away from that, some kind of wind event, or even maybe an explosive event past supernova or nova or something. So that is one of the speculations, is that this is a feature that is broken off from some of the other larger structure of the disks and the gas.
Right. So yes, this could be a possibility. And what about the disk being a part? The kinematics would be similar to that of this molecular disk. It's a disk of molecular gas and dust of within 200 parsecs, as far as I remember, around the supermassive black hole, around the center.
Yeah, that's
speculation in this direction or not?
That one, that one's a little bit more of one that we haven't necessarily considered directly because of the larger distance involved, and also the observables of that molecular disk are quite a bit different. These X7 is not detected in molecular hydrogen.
Wow.
It's only the combination lines. It's much more excited gas. So it's gone through some kind of shock or radiation that has excited the gas. We see some forbidden lines, iron 3. We see some helium, but we do not see molecular features. So it's a little bit different in nature, and so we kind of, and it's also very, very closer to the black hole than the rest of that molecular disk. So.
Right. Okay. Thanks.
Thanks, Betty. I myself, I have a question. Is it possible to estimate the temperature from the dust thermal emission from the gas in the atmosphere of this object?
Yes, we did fit a black body to the spectral profile, and we estimate that the dust temperature is around 500 Kelvin.
500, right.
Yes.
And it's possible to use this with the study of the lines to estimate the density?
That's correct. We've used that. We've used the emission density of the hydrogen and the volume, knowing we know the distance and we know so we were able to estimate the volume and the density to get a mass. And so I'm trying to remember some of these numbers, but the mass we think is on the order of 100 Earth masses, or on that sort of ballpark. So we think it's pretty low mass, but dense enough to have this thermal emission and gas emission.
Right. It's a really intriguing object. Maybe some anybody or hydrodynamic modeling could also help to unveil the nature in the future. Right. Questions more? One question here, Maria.
Yes, thank you for this great talk. I was wondering if there is other instrument that has the capabilities to observe this object, or maybe no, because it's so small. Can you comment on this? And maybe at other wavelengths.
Yeah, that's a good question. Another instrument that we have that we can use at Keck with adaptive optics. So you have to have the adaptive optics in order to distinguish this feature from the other ones. You need the high spatial resolution. But one of the things we wanted to do was get a spectrum of the features at the longer wavelengths and look for some signatures in the dust that might help explain what X7 is made out of, and whether there's some from 3 to 5 micron spectroscopy, you can sometimes get some information about the dust, the grain size, and the chemical composition. And so we tried to do that with an instrument called NERC2, which is a high spectral resolution infrared spectrometer that goes out to 5 microns. Unfortunately, the thermal infrared emission from this object isn't bright enough to do a high spectral dispersion and get any kind of sensitivity to it. So we were unable to see any of the details of the dust features. But that is another instrument that we tried to use to try and understand it.
I see. And what would be for you like the best data that you might have to see, or what are you expecting to have, so you can say, okay, this is this object is this, and it's coming from this other, I don't know, structure.
Yeah, I think
what is missing, I guess, would be the question.
Yeah. Well, I'll be curious to see what JWST shows in the longer wavelengths around this region. It won't have as good a spatial resolution as we see, but it will have better bandwidth coverage in the thermal infrareds and may expose some clues as to what's going on here. ALMA data might also help to understand some other things about the winds and the magnetic fields and things like that. So there's all kinds of different things that might piece together individual clues as to why it looks the way it is and where it came from. So the other thing that I think will help a lot is to continue to monitor it, to get better fits to the orbit, to see if the tidal stretching continues the way we expect, and if it starts to break up. I think that will help understand at least some of the dynamics that are going on. Maybe not the source, but if we understand the dynamics a little bit better, we might be able to trace that back in time and tell kind of where it came from, and that might help distinguish sources or help eliminate some sources too.
Yeah. Okay, thank you.
Okay, so if no more questions, I would like to thank you again, Professor Randy.
Thank you very much.
And I would say we appreciate a lot you sharing here your research and also your knowledge and experience with the Keck Observatory. And we appreciate a lot you are doing this at 7, 8 a.m. now. Thank you very much.
Yeah. Yeah, thank you very much, and hope to do it again in the future.
Thank you.
Bye for now.
Have a good day.
All right.
So for those who are here, we should have a